workshop. We are going to have Richard Eisenberg, who is going to give us some examples of what GHC8 can do.
Thanks, Stephanie. I wanted to talk a little bit today about seeing what, exactly what Stephanie said, what GHC8 can do. And so this is all going to be about dependent type programming in Haskell, right? Because we want our dependently typed language. There. We want our dependently typed language, right? And so we want Haskell. We have it. Wait. Not quite. So GHC8 does not have dependent types. But what it does have is with the support for type and type, I now have this conjecture that anything that you can do in these other languages, you can do in GHC8 and have it still retain all of its types. So I'm not just saying translate the terms. Of course we can do that. But I'm talking about really do this. Except we need singletons. And I'm seeing people grimace. I grimace too, right? So I don't like singletons any more than anyone else. It's just better than not having types, right? And it also requires a bug-free GHC, which is by no means assumed. And so I'm hoping type and type, it actually works fairly well, but GHC 8.2 should have a bunch of, as Simon was saying this morning, is a consolidation release. There's going to be a bunch of type and type fixes, and it'll continue to improve. So what we're going to do today is 3 examples. The goal of these examples is not so you understand how they work. It's to give you an idea of some of the things that are possible with dependent types in Haskell. So these examples all work on GHC8, and so this is stuff that we sort of can do today, although I don't suggest doing it in a production system. So we'll see, well, you can read that, we can read it up there. I'll get into them as we get there. 2 disclaimers here. So there is lots of magic going on behind the scenes. I'm happy to explain the magic. All of the code, I don't know if you saw it sort of in the opening slide, this is all available up on GitHub. So some of this has been massaged to make it look nicer, but it actually is all doing what I say it's doing beneath the scenes. It's just some magic. There's one small bug fix over GHC8. My hotel finally gave me just enough internet so that I could commit this last night. So it's now in head, the bug fix. I'm quite pleased about that. So also, I want to introduce this type here. So as we've seen all week, every dependently typed talk this week has involved this, except for this talk. No length index vectors. We can do other things with dependent types too. Okay, so here's the first example. This is a dependently typed database access program. And so those of you familiar with Uri and Suistra's Power of PyPaper, this is directly inspired by the formulation of dependent types, or a dependently typed database access from that paper. And so let me first show you what it does. This program actually does compile and run. So I can run it. The idea is that I want to know if I type in the name of a professor, I get that professor's students. So pretty simple program. The idea is, we can see at the bottom here, there's 2 different database tables that it's working over. So there's a classes table with this schema. So in this example, I'm just using flat text files for my database, but I could use real database. That's not actually the interesting part here. The professor's name is a string. The students is a list of int, which are their ID numbers. And then the name of the course is also a string. We're not going to use the name of the course in this example, but it's to show that we can actually have more columns that we don't use, and you'll see how that's interesting in a few minutes. There is also the students table, which looks like this. So we have the student's last name and first name, their ID, so that's going to hook up with that list of int that we saw in the previous schema, and their grad year, not important for this example, but still in here show we can have other things. So let's look at the code here. And so one interesting thing I'd like to point out is this big function that does all of the work this readDB, it has no type signature. And that's one of the interesting things about this example, and different than those other dependently typed languages, in that we can infer the type of a function like this. And so actually what happens is that there's this, well, we read in the tables, we do some simple I/O. This really is put string and get line that we all know and love. It's nothing strange going on here. And then there's this big query, but what we can do is, if this query is well typed, then we know certain things about the schema of the tables. And so in fact, we can ask what the type is of readDB. And there it is. Now that's big and a little bit confusing, but that's actually the point. We're trying to capture everything that we need to know about the schemas in the type, and this is all done by inference. And so in this query, and due to lack of time, I'm not going to sort of walk through everything that's going on here. One thing that we can see here, I'll just sort of point out one detail, is here we want the prof field to match that literal prof variable that I assigned with getLine a few lines previous. And so that means, in particular, that we must have a prof field of type string in the schema. And so it can infer that by looking at this query. So all of the other constraints just come out of, what do we need for this query to make sense? So there's another fun feature here is that when I project out the name, I don't even have to say what I'm projecting, because I say up here in print name that I want it to be a name. So type inference does the work for us, sort of nice features like that. So then let's look at how this function gets called, right? Because before I can call readDB, I need to be able to satisfy all of these constraints on the schema. And so here, what we need to do is we need to check that the schema actually matches these constraints. So one interesting aspect of this example, and unlike other places where we have dependently typed database access, so actually when I was sort of looking for related work, there's this package called Opali, which actually uses a very similar model to what I'm doing here. But one of the minuses to dependently typed database access is you often have to repeat the whole schema in some form in your code. And maybe you have some tooling to automatically move it in and out and such. But here, the full representation of the schema appears nowhere. And so an interesting aspect of this is that when we, if there's something wrong here, if my query doesn't make sense for my database, I'm not going to get a compile time error. Because maybe that query makes sense for some other database somewhere else. And so it still is a runtime error, but it's a runtime error when loading the database, and not when executing the query. So the queries are guaranteed safe, but this check schema operation is not necessarily. The schema might not match the inferred one. The other thing that we see here is there's some weird template Haskell going on, right? So what this is actually doing is the template Haskell code looks up the inferred type of readDB and then uses that to generate a bunch of calls to functions to guarantee to check the schema against this. And so one of the aspects of this example I really like is that it shows why doing dependent types in a large language with lots of features is really cool, because we can use them together. So here, because I have this template metaprogramming language, what I can do is I can reify the type of readDB and then use that to generate the code. And so under the hood, to make this all work, I need a whole bunch of dependent types, even though we don't see any right here. And that's another nice thing about Haskell, is that we can have a complex dependently typed library, but the surface doesn't have to be quite so bad. Okay, so there's lots more I could say about this, but I want to move on to the other examples. We can come back at the end with questions. I'm always worried about time, so I'll take questions at the end, unfortunately. So my next example comes out of work I was doing with Cheyenne. Is Cheyenne here? No. Okay. He has a talk later today about, among other things, extensible data types. So the idea here is that I have two mutually recursive data types. So this is a tiny slice of Haskell, right? So we have variables, function applications, lambda abstractions, but the lambda abstractions are over patterns, not just variables, as well as integer literals here. And then my patterns are very simple. I can have a variable pattern or a view pattern, chosen just so I have these two mutually recursive types. And so in here I can have an example. Here's an example of something that I can encode using this AST. And just to prove it, you know, this is there's nothing very fancy here. But now I realize, well, this AST, that's been parsed nicely, but I want to be able to type check that thing. And so when I type check it, now we have that initial AST. Well, and then after I type check, I want to add a new field to this constructor. I want to know the type of the pattern in a lambda binding. And whenever I bind a variable, I want to know its type as well. And so I need to add these extra fields. But to do that, I had to make whole new data structures. And now I have two mutually recursive, or two sets of two mutually recursive data structures to work over. And they're totally different. And that's a bit of a pain. And then below I have the examples again. That's just to that's more to check myself to make sure I've done this correctly. Not very interesting. So then here now, after type checking, I need to desugar. And here I'm doing this very strange thing, desugaring into having this new operator. So if I have a plus, I'm actually going to represent it with the Haskell function plus. This is not what a real compiler would do, but it's a toy example. Let's just go with it. But what I've had to do here is I've taken everything I've just done and now I've added a new constructor to my mutually recursive data types. So now I need 3 versions of them. And this is really annoying. But in fact, this is not so far from what GHC does right now. We have one data type, but then there's a bunch of constructors that aren't used, and a bunch of fields that aren't used, and there used to be bottoms stored in these spots that would then break whenever anyone walked over the AST. It's gotten better, but it's still a little bit confusing. And so the goal here is to go to something like this, where we have an extensible data type. And as we look at this, there's going to be a fair amount of boilerplate, and the idea is in the end, the boilerplate will get generated. And so this isn't the code that we expect people to write, but maybe there's some surface syntax that gets desugared into something that we're seeing here. And the idea here is that I'm going to parameterize my data types over an extension function, and the extension function is told what we're extending. So here, this is the extension for variable expressions. And this is the extension for lambda expressions. It all refers to this data type tag, which appears up here. So there's one big data type that describes everything I could possibly do. And then down here, there's concrete instantiations. So I'm using data families to do this. So a parsed, do I need to add anything to a parsed variable? No, so I just have a constructor that takes no arguments. And do I need to add anything to a parsed application? No, so I have another constructor that takes no arguments. And on the other hand, if once it's type checked, well then this lambda, that will take an argument. So that's how I get that type in there, because I'm going to have an X checked. The minus to this approach, other than the boilerplate, is that we end up with this one monolithic tag type that has to have all the tags. So if we imagine lots of mutually recursive data structures, that's no good. But I can't split it up, because if I split it up, then here, where is it? Here, where I have a pat inside of an expression, or an expression inside of a pattern, the kind would be wrong if I had 2 separate tag types. So what this calls for is a higher rank kind. Clearly. And so now, I can have 2 separate tag types. I can have an expression tag type separate from my pattern tag type, so it doesn't have to be commented into one module. And then I can parameterize over a higher rank, a type variable of higher rank kind, X. And so this can get passed back and forth, and I can use all of these tags. And all I have to do down here is to just declare my data families to also be higher rank kinded. And this all works. I've just compiled the file. We already have higher rank kinds. So there's not even any singletons here. And so that, I think, simplifies things. So now we have an extensible data type where we still have some notion of modularity. We can actually go one step further than this, because the X that I have here, maybe I accidentally specialized that to bool arrow type, and I really only want it to be this E tag and this P tag. So here, well, now I have a tag which chooses between the expression tag and the pattern tag. And I have a type family tag, which chooses between these. And then now my higher rank kind, my type variable of a higher rank kind can use that type family to choose which one. And this also works today. So I use a higher rank kind and a kind family to get the job done. And it actually has to be an injective type family to allow inference to work around when I use a specific var tag. I need to know which tag is associated with var tag. And so that requires the injectivity constraint. So is this really the right answer to the extensible data types? Probably not. But we went through this design legitimately in looking for the right design. We did not come to this as looking for an example of a higher rank kind. It came out naturally. So this is something that we can do. Maybe it is the right design. I don't know. There's a lot of boilerplate here. Okay, so, oh good, I'm actually doing better with time on my clock. So let me go on to the last example, which is here. So in this example, some of you may remember Edwin Brady's paper at ICFP 13 talking about Idris's extensive modular algebraic effects library. And Edwin talked about how one of the points of Idris was to be able to write a library like that. Well, I've translated now the library into Haskell. And this translation went so smoothly, I still don't understand really how the library works. But what that means is that it's just mechanical. I can just take I took the Idris definition and I just translated it to Haskell and added a whole lot of S's, right? So there's a lot of singletons in this one. But the translation is faithful, and it works the exact same way that the Idris library works. And so what this allows us to do is now, instead of having a stack of monad transformers, I just have an effect type, which is parameterized by the list of capabilities. So this example, let me compile that, and I can run it. And so say I want to throw 2 dice 100 times, and it will throw the dice 100 times and give me some output. So this, this is a real program. I can compile this into a binary and run it, even though it's working with all these dependent types. This exists for real. But I might look at this output and say, something's very wrong, right? The mean value after throwing 2 dice 100 times should be 7, or quite close to 7, and this is not that close to 7. And so that's no good. So now I decide, well, maybe I want to keep track of how many times I throw a 6. And so that's quite easy to do. I just add state. And I can say here, update the state with, I'm going to add count equals 6 rolls. So I can say that. Now this won't compile because I need the state up here. And then let's see, what else? Oh, I need to give it the initial state. So when you use this effects library, you have to there's data associated with each effect. And so I'll add my initial count of 0 here. And then I can just print it out. Let's see. And so I have to actually say the nat here because maybe I have state with various different things in my stack, and so I need to give type inference just a little hint there.
That wasn't possible with the monad transformer.
What was that?
That was not possible. Using the type as a key for us.
Yes, I know. So, and now I recompiled this program, and then I run it, and then we get 23 6s, which isn't quite right. And the reason for this is that I did a terrible implementation of pseudo-random numbers under the hood here. And that's because actually all of my numbers are unary, so I didn't want to do a real implementation. But it shows how this can work. And then let's say we want to remove this, and so forget about this. And so I remove the state. Still compiles just fine, right? Because what's happening here is that there's a lift, which just takes any list that's a sublist of another and sort of sorts it all out for us. And so because the type, let me recenter this. because the type of throw dice does have a different effect list than the type of main, I do need the lift. Idris is awfully clever here, and they have a facility for when there's a type error that they can actually, you can add features to Idris to inject some code, and GHC doesn't do that yet. Even type checker plugins aren't quite that strong yet. But you still only have to say lift once. We don't have to lift many times, so I think that's pretty cool. There might be a better way of designing this if we were designing from scratch from Haskell. My goal was really to just take the Idris library and see does that translate, and yes it does. Okay.
Visible type application.
What was that?
Do you need the visible type application on the next slide?
On which line? Here?
Yeah.
I'm sure I do. Something terrible is going to happen. That.
Just like Idris.
And I think that you might be able to redesign this so you don't need that. That this could be more inferred. But again, coming from Idris, they're expecting that you always know. Because Idris doesn't infer types. But even in Idris, right? What was that?
Sometimes it does.
Sometimes it does. But am I right that I need to give a type annotation on starting end in Idris?
Yes.
Okay. And so we've gone a step further here in this one small way. So let me go back to the slides one last little bit. Okay. So where are we? I said we don't really have dependent types, even though I've shown you all these dependent types. So the theory, yes, I think I've sorted the theory out. There's some light reading there if you want to see it. There's some people in the room over here who know quite how light the reading is. Implementation. I want to be honest here. I'm starting a new job. There's other research to do as well. This will happen. It's definitely going to take at least 2 years. And so we're looking, GHC 8.6 at the earliest. But, of course, I would love help with all of this. Something I've been thinking about, and I've actually gotten a couple of concrete ideas this week of ways to slice this large problem into smaller pieces. So maybe I can farm out some of these pieces and we can get there sooner, or more likely, be more on time for the 2 years. So it's quite a bit of work in this, but I think we really are going in this direction, and it's very exciting. And so that's all I've got. Thanks very much.
Okay, time for just a few quick questions. So over here.
So in the lambda calculus or the expression language example, can you?
Yes.
So the way I would like to write that is to be able to say that tag is a star, and then e tag is a tag with these constructors. So e tag is a type of kind tag with these constructors. B tag is another data type of kind tag with these constructors, and then in expr or whatever it was called, I would like to say that instead of a for all, I would like to say that it takes an x which takes t of type or kind tag and tt of type t into a star, because that way you wouldn't have to have all this open. Like, it seems to me that this is. It's not only that it duplicates a lot of things, it's also very open. In this case, I think you would want it to be closed. So my question is, would that be possible to write? Like, could you write something like, it takes t of kind tag and tt of kind t and to star?
Well, I don't think so. That's something we can look at. I think that the reason, it sounded like what you were saying in there is that you wanted a type that has values, but that type has a kind other than type.
Yes.
And I'm not exactly sure what that would mean, sort of from a theoretical standpoint, or so that sort of takes us away from sort of the idea of having a set of sorts that we can work with. So we can talk about that a little bit, but I think that sort of moves things in a slightly different direction. So the answer is no, we can't do that.
Okay, Yoki.
In the code once before that, or also here, we have this type little function with a for all, and as a Haskell programmer I see that I think that's can't really do anything, there's not pattern match on the tag, but you do. So does this mean that the type little programming language that we see here is completely different than Haskell, and we have to basically forget everything we know about polymorphic and parametricity and that kind of stuff?
That's a great question. So that shouldn't have been spelled for all. That should have been spelled pi. So dependent Haskell, you know, there's a talk, I don't know, a few years ago in this venue. There's going to be a separate for all and pi, and this really is a pi and not a for all.
So I remember in Edward's Extensible effects library, we had some ifs on the type level to do conditional, like I can't remember exactly, but do you have those conditionals in your
Yes.
effects library?
Yes.
What do they look like? Can you actually do if on the type level?
Sure.
Is it like type level?
Yes.
Right,
Yeah, yeah.
Type family if.
It's actually it's you already have it. Import data.type.bool and then exports if.
Oh, really?
Yes. That's shipped with GHC.
Okay, last question, Leonard.
Can you do printf now?
It's a good question. I haven't tried. Probably. According to my conjecture, yes.
Okay, let's thank Richard.